century BC, in the Egyptian city of Alexandria, a great mathematician, Eratosthenes, measured the size of the Earth using just a plain ordinary stick. He read that in Syene, which is 800 kilometers away from Alexandria, on June the 21st, the day of the summer solstice, the longest day of the year, at noon, vertical sticks cast no shadows at all, whilst he knew that at the same instant of time in Alexandria, vertical sticks do cast a definite shadow. He reasoned with a model like this. Assuming the Earth is flat, and I thought it was at the time, vertical sticks cast shadows of equal length, the sun being very far away. And if a vertical stick casts no shadow and in two places, that's also easy to understand, providing the sun is directly overhead. But how could it be, he reasoned, that at the same instant of time, a vertical stick casts no shadow in Syene and a definite shadow in Alexandria? The answer to this, Eratosthenes thought, was that the Earth is curved, and the greater the curvature, the greater the difference in shadow lengths. He imagined the Earth to be a sphere. The sun is so far away that its rays are parallel when they reach the Earth. The sticks placed at different angles to the sun rays cast shadows of different lengths. If the two sticks are projected to the center, they would intersect at an angle, which is the difference in the latitude between the two places. From the shadow length in Alexandria, the angle A can be measured. If two parallel straight lines are transversed by a third, the interior alternate angles are equal. Eratosthenes measured the angle A from the shadow length in Alexandria and found it to be just over 7 degrees. He knew that the distance between Alexandria and Syene was about 800 kilometers. Now 7 degrees goes into 360 degrees about 50 times, which corresponds to 800 kilometers times 50, or about 40,000 kilometers. So that must be the circumference of the Earth, thought Eratosthenes. We now know that he was only about 50 kilometers out. The most common use of numbers is to represent points on a line, and we call such line a number line. Now here we have an example of a number line. If we take a unit measurement, let's say this is the unit measurement, and we mark off a series of points corresponding to this unit measurement along the line, we will finish up with dots. We use these dots to represent the points, and we use numbers corresponding to these dots to represent the points on a number line. So we count the numbers in a natural way. That's one unit, and that's another unit, and another unit. So we use these whole positive numbers, which we call integers, to represent these intervals. So therefore, we have that number 1 corresponding to that point, number 2 corresponding to that point, number 3 corresponding to that point. And in this manner, we can construct infinitely many points in that direction. This arrow here indicates that this number line goes on forever in that direction. Now, if we use the same process and mark off the same unit interval to the left of the origin, then again we will finish up with a series of counting numbers, whole numbers, or if you like, integers again, and this time, to emphasize that it is in a different direction, we use a minus sign. So therefore, -1 corresponds to that point, -2 corresponds to that point, and so on in the negative direction. In this way, we have created a whole family of numbers, which we call integers. We denote integers by a symbol j, and j plus corresponds to the set of positive integers. These are the integers to the right of the origin, and we use j minus to represent the set of negative integers, and of course they are to the left of the origin. And in this way we have a set of integers. And as you can see, this is an infinite set. It goes on forever in both directions. Now, between any two integers, there are infinitely many points. For example, take this interval here. Between 0 and 1, there are infinitely many points. And we can divide that interval into any number of parts. Consider a straight line of unit length. Suppose we wish to construct the rational number 1/3. Using similar triangles method, we divide this line into 3 equal parts and denote the corresponding point by the rational number 1/3. I can point to it and say the number 1/3 belongs here. Suppose we now wish to construct 3/4 on this line. This time we divide the line into 4 equal parts, using the same technique. In fact, using the similar triangles theorem, we can construct any rational number on a straight line. This brings us now to a set of rational numbers. A rational number is a ratio of two integers, and we usually represent this relationship by a formula, where R stands for rational number, which is equal to the ratio of two integers P and Q, where P and Q are members of the set of integers, and Q does not equal to 0. Now, we can look at rational numbers as an extension of the set of integers. For example, if we take an interval between two integers, or say between 0 and 1 in this case, as I have done, and divide this interval into 3 equal parts, then we will get a point corresponding to 1/3 and a point corresponding to a fraction 2/3. Now, a number such as 2/3 or 1/3 are examples of rational numbers because they are a ratio of two integers. 1 is an integer, 3 is an integer, so 1/3 is a rational number, and it corresponds to this point here, and 2/3 is a rational number which corresponds to this point here. Now, in the same manner, we could divide this line interval into 4 parts or 5 parts, and then we will get the fractions like 1/5, 2/5, 3/5, etc. So in this manner, as you can see, we can construct any rational number on a number line. And the essence of all this is that a rational number resides on a number line with all the other numbers. Irrational numbers are not rational. That's what it means. Irrational number is not a rational number. That means it cannot be expressed as a ratio of two integers. We can construct an irrational number in the following way. If you consider a square with the base 1 unit, then if the base is 1 unit and the height is 1 unit, then we can calculate the length of this diagonal using Pythagoras' theorem. Let's suppose that we denote this diagonal length by x. Well, then we can write, using Pythagoras' theorem, the relationship, the square on the hypotenuse is equal to the sum of the squares on the other two sides, so that means x squared will equal to 1 squared plus 1 squared, which means that x squared is equal to 2. And that means that x is equal to square root of 2. Well, now, nobody's been able to find in the whole of history two integers so that when they're divided they will give us square root of 2. There are no integers, p and q, which when divided will give you a square root of 2. So that means square root of 2 cannot be expressed as a ratio of two integers p and q, where p and q are both members of a set of rationals, such as, for example, we've discovered earlier. 1 on 3 is a rational number, 2 on 3 is a rational number. But square root of 2, which is the length of this diagonal, is not a rational number. Now, if we take a compass and using this length here, which is square root of 2, we drop it onto the axis, then we will get a point here which corresponds to square root of 2. And so this point here, which corresponds to that length, this point here is square root of 2, which is an irrational number. And in this manner, we have constructed an irrational number on a number line together with other numbers, such as an integer. 1 is an integer, 2 is an integer, 1 on 3 is a rational number, 2 on 3 is a rational number, and here we have an example of an irrational number. So you can see that irrational number lives very happily with all the other numbers on a number line. Now, the consequence of all this is to demonstrate that an irrational number also resides on a number line together with all the other numbers. In this lesson, we studied the elements of projective geometry, and we learned how to divide a straight line into any number of parts. This has a practical application based on the use of ratio and proportion. We geometrically constructed a rational and an irrational number on a number line, and we looked at two of the most important theorems in geometry: the similar triangles theorem, attributed to Thales, and the great Pythagoras' theorem. Geometry persists in nature and is a powerful tool in the art and the science of measurement. And that's what geometry is: geos, the earth, and metros, to measure. A little square in the middle, which we will fill in here with this little black square.